Hey guys, so welcome to my sixth and final video in my binomial tree option pricing series. In this video, I'm basically going to show you that the n-step binomial tree model we implemented in the last video in Python converges to the Black-Scholes formula for European call and put options as the number of time steps n goes to infinity. In this video, I'm going to show you the numerical version with Python to give you guys to convince you guys empirically that it works, but you can actually prove it exact with real limits and stuff like that. And I'll give you a few hints. You're going to need to use the central limit theorem to basically argue that the binomial distribution is normal when n is large. And you're going to need to do some Taylor expansion on the exponentials in the risk-neutral probability. And with those things, you can get to Black-Scholes formula. If I get enough people asking for it, I will make a video on it. But for now, it's a lot of work. So let's get started, and we're going to do the empirical validation. So I'm just going to copy. This is what we had in the previous video. We had the binomial tree model. We had a function called binomial tree price that gives you the price of European call or put options or American call or put options with the binomial tree formula. So remember last time we had we had these parameters. We had the initial stock price is 100. That means S is 100, K the strike is 105, sigma the volatility is 0.2, R the risk-free rate is 0.05, T the time to expiry is 1, and we had N equals 100 time steps. So then we showed the price, of course, for a European call and then American call, which is the same price. Early exercise is never optimal in that case. And then for a American put and the European put. But the American put at a higher price because it was optimal to exercise early. So here, since the Black-Scholes is for European options, I'm going to show you guys just for European options, we're going to vary n. We're going to make n very large, and we're going to show you when n gets pretty large that it converges to the Black-Scholes formula. After I run this, I'll actually explain a little bit the Black-Scholes formula for some of you beginners. But for now, because the n equals 10,000 steps takes some time, I'm going to actually calculate the binomial prices first. So I'll do for n in, let's say, 100, 200, 500, 1,000, 10,000. I'll do I'll do binomial. I'll have a dictionary, which will be binomial binomial call prices, and then I'll do binomial call prices of n equals the binomial tree price, and we're going to always have European, but the first case is going to be call, and what's going to vary is this n here. Okay, so this is the call prices. Okay, so now for put prices, we're going to do the same thing, binomial put prices, and it'll just be put. That's the only difference. Did I mess up? Oops, I called this binomial call prices, so sorry about that. So I'll interrupt it and do binomial put prices. Okay, great. Call prices, and now we'll run it. And in the meantime, while this is running, I'll give an overview for beginners on the Black-Scholes formula. So it's the famous formula for option pricing, assuming stock prices follow geometric Brownian motion. I will make future videos on those concepts, but it has a lot of assumptions, like basically no transaction costs, no taxes, markets are frictionless, like no bid-ask spread, no arbitrage, complete markets, risk-free rate and volatility are constant. So there's a lot of assumptions. Anyways, this is the famous formula for calls and puts. So n is actually like the cumulative normal distribution, and it's applied to this D1 quantity, which is the log of the initial stock price over the strike plus risk-free rate plus volatility squared over 2 times time to expiry over volatility times square root of time to expiry. And D2 is basically D1 minus volatility times square root of time to expiry. So these are weird concepts, but just to give you some intuition, we know that if the stock price goes to like very high, like infinity, and let's say forget the risk-free rate, let's assume it's 0, the call price is S minus K, right? So if the stock price goes to infinity, this ln S0 over K goes to infinity, and these are just small things relative. So D1 is infinity, normal of infinite, cumulative normal applied to infinity is 1. And then the D1 minus something, so infinity minus something is infinity. So this will be also 1, so it would be basically S minus K. And now if the stock price goes to 0, the value of the option is going to be worthless. So just to show you guys intuitively, if S goes to 0, this ln of 0 over K goes to minus infinity. So this will be minus infinity. And the cumulative distribution of minus infinity is 0, so this is 0. And similarly, this minus infinity minus a small amount would be minus infinity. So this will be minus infinity, so it'll be S0 minus K if you make the risk-free rate 0, just for intuition. So, sorry, it'll be S0 times 0 minus K times 0, which is 0. So that makes sense, just as intuition. So these did compute. So I got the binomial call and put prices for various number of time steps. So binomial call prices, and here's binomial put prices. So now, if we implement this Black-Scholes formula, we'll see that the prices are similar. And you know what? Because this finished so fast, let me actually, let's just add, maybe we'll add 20,000 steps. We'll add it for the put, because I know for the call it doesn't really matter. But for the put, let's add 20,000 steps. And let's run this still in the meantime while I'm implementing this. So let's implement this formula really fast. So we'll do like def Black-Scholes price, and then similar to the binomial price, so we have all our inputs. We'll have S, K, sigma, R, T, but we don't need style. It's always going to be European, so I'll do BS price of this. And then I'll do similar to the last video, assert kind in call put. And then I'll do something like this. I'll do D1 equals this, D2 equals this. What do we need? We need the cumulative normal, so we can do that. We can do from Skippy. What is it not? Oh, maybe it doesn't give me autocomplete because the other cell is running. So if I remember correctly, it's from skippy.stats import norm, and then it's norm.cdf is the function .cdf, but let's call it n. We can do this just to make the notation fit with this thing here. So so what's d1? D1 is np.log s over k plus r minus, or is it plus sigma squared. Sigma squared. I thought for a second my recording ran out of space. Over 2 times time to expiry is t. I hope I got that right. And then divided by sigma divided by t. This should be d1. Divided by sigma divided by square root of t, sorry. np dot square root of t. I probably did it wrong. So this d2 is going to be d1 minus sigma times np dot square root of time to expiry t. So now we have our d1 and d2. So the formula is basically s times n d1 minus k times np dot x negative r times t n d2 if if kind equals call, else it's going to be basically the put formula, which is basically you have a k here and you have a negative d2 k times, you basically flip them with a minus sign kind of. So you go like this. I have it above, of course. negative nd2 minus s times negative nd1. I probably made a mistake, but it should be this. So that's what we're going to return. And let's see if this works. So I'll do, oh, it's still running. It's probably stuck on the 20,000 case. So for now, let's make sure we got it right. We got log of s over k, r plus sigma squared over 2 times t over sigma squared of t. d1 is this guy. And this should work. I decided to give you 20,000 steps, so it's taking longer. But anyways, for comparison purposes, I do want to round to the nearest 4 digits anyway. So I'll do 4 n steps. Remember, we have n steps. Option price in binomial call prices. The items, and then I'm gonna do print f num steps steps. Let's do num steps n price. What's the price we're gonna have? We'll have the price be option price. But let's round the price. So actually you can round it directly here. If I remember, how do you round f string? You do like, I'll do like round, oops, I don't have internet. Let's forget, you can round the f string. I just don't remember it off the top of my head, but I'll do np.round 4, the nearest 4 digits. Here, and we're going to do the same thing for the put prices, binomial put prices. Okay, and it finally ran. Sorry for the delay. Let's get the Black-Scholes BS call price equals this, BS put price equals this guy. Equals this guy with put. Great. Now, do we have the answer? So now let's print this out after. I'll do print BS price. And then I'll do BS call price. And then I'll do, here I'll do BS put price. Anyways, I'll put this code up. What did I do wrong? No steps. Okay, so you see, let's round this baby also to the nearest 4 digits, just so it's easier to look at. So if this convinces you, n steps, sorry. So look, if this convinces you, this is for the call option. It starts off not being the same as Black-Scholes. It's 0.026, so it's off by a decent amount, but then this gets smaller and smaller, and then too small, and then eventually gets to 8.0214, which is the Black-Scholes price. Now let's try for the put option. Let's see how it looks like. Remember, this was a mess up, so we need n steps. And let's do np.round 4. I don't know what the answer is for 20,000 steps. Okay. Anyways, see, I knew we were gonna get close, but not close enough. So it starts at 7.9053, which is pretty different than the Black-Scholes 7.9004, but eventually it gets to 7.9005, and it kind of, I guess, never quite gets there. It'll eventually get there. It could be off by some numerical stuff. Anyways, hope you enjoyed this video. I'll post it if you're new, and please like and subscribe, especially to these videos, because I'm barely getting any views on the binomial tree thing. So anyways, thank you guys, and see you guys in the next video.